8.2, exponential functions. Exponential function, it takes this kind of format, and in actuality, it kind of takes, like this is the foundation for it, but usually there's kind of a value that's in front there. I put an A there because that's the letter that they generally use. That's the y-intercept for these exponential type functions. Now we have been dealing with exponential functions, but they became parabolas. You can see that these types of functions create these types of graphs, and they can move, right? They can go up and down, but if you look at this graph right here, as you go to the left, which is unusual, but if you go to the left on this one, you get really, really close to the x-axis. That's telling us that it will never cross the x-axis, meaning you can get values so small that they may seem like zero, but not quite zero, mathematically anyways. And if this graph right here, if you were to go to the right, it gets really, really close to zero. I mean, just because of the thickness of the lines, these two look like they're touching, but they never actually do touch. So that creates what we call an asymptote, which is a cool word to say out loud to people. Go and call people asymptotes and see how that goes. So that question, is it a times b to the power of x, or is it just b to the power of x? If you just keep it as b to the power of x, a is 1, which is why these y-intercepts are showing as 1. If you don't want to show that 1, you can make it a phantom 1. But if it was moved up, like up here, let's say it was up here at 8 maybe, then you'd have 8 times whatever the base is to the power of x. These are exponential functions. Exponents mean that we are repeatedly multiplying by something, and graphically that's what creates a curve. In the past, when we looked at straight lines, this is before parabolas, but when we looked at straight lines, that means you're adding the same value over and over and over, which is that's how we get the slope. And the slope is the same for any straight line. As you go through the line, its slope is the same. But you can see these ones, it's curving, because right here you could multiply by 2, and then you get 2, and then you could multiply that by 2 to get 4. 4 times 2 is 8, and you can see those numbers are going up, exponentially, as you continue to repeatedly multiply. That's why this is a B. B is for base. And for exponential expressions, the number that's being repeatedly multiplied is called a base. So it's a base to the power of x, but it's multiplied by some kind of starting value, which is the y-intercept. So again, the basic form of this function takes a y-intercept of 0, 1, but that can change, right? Again, if it's moved up or down, and I guess upside down, you can. But that all reflected in the a value. Since these are not linear, we'll need a table to graph these equations. Yeah, the table is very nice for the graph. What this means also is that you are going to have to choose your own x values. So some personal responsibility? Absolutely. Are you adults? We expect it, hopefully, by this time. So choose your own x values. That's great. Now, I did say this word asymptote, which if you talk to a math person, it'd be like, oh, thank you very much. But again, on the street, maybe not as well. But I recommend doing this for 3 values. I think on the assignment, you only have to do 2, because electronically, it's like, just put 2 points on the graph. I don't really care which 2, and then it knows what to do with the rest. Again, the 2 values is nice for a pattern, but if you put 2 points on a graph, you can make a straight line through those. So a third value is nice, especially if you're doing it by hand, because it confirms the pattern. If this were a test, then you would want to put as many points as you can on the graph, so that it gives you, again, the pattern, but then it'll make your drawing a lot better. You've seen my drawings; they suck pretty bad, but I'll try. Let's describe asymptote a little bit better. So an asymptote is a straight line. For the ones that we're looking at, it's usually horizontal. Okay. And the asymptote for this specific line, again, like I was saying, it gets really close to 0 right there. And so, but it never actually crosses 0. It gets so close to it, it may even look like 0, but it never is. And so for this one, the asymptote is actually just the x-axis. But if the graph were to move up or down, which it can, then sometimes the asymptote may be up here or down here. What we know from this is that asymptotes, if they're horizontal, like the ones we're going to be seeing, the asymptote takes an equation of y equals. Usually it's some kind of value that's added to the exponential function or equation. So I like to show it as a times b to the power of x. You don't really need the a, but you can. Now, if you add or subtract anything to that, let's say you added something to that, like c right there, that's going to move that graph up. Again, if c was negative, it could move it down. But the y value is whatever's being added or subtracted to that, because I can get this right here to be very, very, very close to 0. But if I'm adding something to that, then it means that I'm getting very close. Not the whole y is getting very close to this c value if this is getting close to 0. That is what an asymptote is. Well, for that one, couldn't you just say that it's down here because it's never going to cross that line? Yeah, but down here, this purple line that's drawn, it's not ever going to get really close to this one. It does get really close to this asymptote, though. So that's why this one, the second one that we drew right there, no good. So in graphing these, we first need to just make sure that we can evaluate them, which, as it turns out, my calculator loves to do for me. And I love that it does it for me. So thank you, calculator. But this one is saying that we want f of negative 5, right? So this is telling us, hey, your x is negative 5. So in your function, for f of negative 5, we're going to take that 750, multiply it by 1.15 to the power of x, but our x is negative 5, so the x gets replaced with negative 5. Can you put a negative exponent in the calculator? Absolutely. And the calculator appreciates it if you do, because it loves it so much. So thank you, calculator. Again, 750 times 1.15 to the power of negative 5. Enter. And this is what my calculator says it is. And I trust my calculator, by the way. 372.882515. I'll keep this number just because it's kind of ugly, actually. I'll round it. So I'm gonna round this to the nearest hundredth. So the 8 in the hundredths place value stays an 8 because in the thousandths place value is 2. And my answer I'll just rounded it, right? That's what I get. We know how to evaluate functions, hopefully by now. If we don't, that's how you do it. You just replace whatever x value puts into the function. That's an input. This is an output, by the way. But this is in order to create your own table so that when you need these values to put in a graph, you can. Meaning that this would actually be the ordered pair, negative 5, 372.88. So like I was saying, you could make a table out of that as well. You could say, well, x and y. And then you could say, well, negative 5, 372.88. That could be an ordered pair that you put onto the graph. Do we really want these decimal values? No, but we kind of expect them because the base here was a decimal value. Now, I recommend choosing easy values, such as when x is, 0, because when x is 0, it gives us nice values to work with. This would mean that you'd have 1.15 to the power of 0, and anything, be careful, because some students like it's 0, but anything to the power of 0 is 1, and so I'd have 750 times 1, which is 750. That's a nice value to put on there. Again, x is 0. 1, is that going to make this better? I mean, you're still going to have to multiply by this decimal, but it may look better than this crap. It's up to you. So here's our function, right? And like I said, we're going to have to choose our own x values in this, and we're going to pretend like we enjoy it. So I always recommend at least choosing one negative exponent. It's a negative 4 to the power of x. Kind of weird on this one. Let me explain what's happening in the function there. It's really negative 1 times 4 to the power of x. Okay, so be careful because the negative 4 is not, the exponent is not applied to the negative. All this is telling us is that the answers are always going to be negative for our y values, which means that we're going to be below the x-axis. We're expecting something down here or something like this. Okay, so again, I'm going to say, let's just start with let's start with something easy, all right? Fair enough. Let's look for our y-intercept. So I'm going to put x is 0 because that's such a nice value to work with. So in my function, then, it would have, again, I'm going to show it as negative 1 times 4 to the power of 0. That'd be negative 1 times 1, which is negative 1. So I get this ordered pair, 0, negative 1, which is right here. Very nice. We got 0, negative 1 on the graph. Okay, and let's stick with some nice values on this. So I'm going to choose x is 1. All right, well, that would be negative 1 times 4 to the power of 1, which would be negative 1 times 4, which is negative 4. So that's an ordered pair at 1, negative 4, right there. Now already I know that this is going to get really, steep really fast going downwards, and then to the left it's going to get close to 0. But I'm going to prove that. The next value probably won't fit on the graph. I'm going to choose x is 2. So that'd be negative 1 times 4 to the power of 2. That'd be negative 1 times 16, which is negative 16. Yeah, this is, again, it's exponential, so it's going to increase very quickly, even if it's increasing the negatives. And I can't fit that on this graph, this specific graph. Sometimes on the assignment, just be careful because they may move this up knowing that you're going to be below the x-axis, and that could fit on the graph. But the one that I have on this classwork here is not going to fit. Now, like I said, it'd be nice to have 3 values on the graph, because if I were just to connect those 2 points, the purple and green point on the graph, you could just say it's a straight line. But it's not. We know it's curved because it's an exponential function. The x is in the exponent. So this is where I would want some other value to use. And I'm going to choose, let's choose negative 1, because that's a nice value to work with. Kind of. So then I would have negative 1 times 4 to the power of negative 1, which is really negative 1 times 1/4, which is negative 1/4. In fact, the fraction there is going to not really help us so much. It may be better to show this as a decimal. Negative 0.25. So let's get this on the graph. So that's negative 1, and I have to estimate this. It's true, but I have to get this point right here. So again, just this much right here is enough to confirm that it is exponential, because between going from negative 1 to 0, it's a very small change in y, but going from 0 to 1, it's a lot bigger than that. So we would expect this then. Here we go. So I got to do this by hand. This is going to get really close to 0 as we go to the left. Now I've kind of pushed that line onto the x-axis. That's just the thickness of the line. I can't really help that. But I've done my best not to cross it. Okay, and then over here on the right, yeesh, gotta get down to negative 16. There we go. So you see I did that kind of little bit by little bit as I went down. You can do it however you need to. What I would caution you on is on this one, right? So we have the 3 points. We got the red one, we got the purple one, we got the green one. Just again, if you're going to the left, don't cross the x-axis here, because that's an asymptote. It cannot cross the x-axis. Again, if it looks like you're trying, like, maybe you crossed a little bit, but then you came back, hey, that's fine. And then sometimes what will happen even on the right, students will be like, hey, something like this. Okay, I don't know what the crap happened. Maybe someone jerked your elbow. I don't know. But just be careful on that. Just, erase and then fix it. I'm not asking for perfection, just something that looks decent.
It never touches 0, right?
Now, by the way, I made my own table. Just so everyone remembers, the calculator knows how to make tables as well. If you use the table function, you'll never guess where it is on the calculator. It's the button that says table. So if you push that, enter this in, the calculator would make the table for you. The calculator graciously has asked us to please show us how to do this. You're welcome, calculator. I will. So we want to type this in the calculator. Like I was saying, if you want to put this in the calculator, you got to find the button that says table. I'm talking about making a table with the calculator, because the calculator is like, please let me do it for you. So I'm going to type this in. When you push table, it should show the y equals on the calculator. Okay, so it's saying please put the function in, because I want to make the table for you. I'm going to push the negative button. This is not the minus button. You got to go to the bottom right of the calculator. Enter. To the left of it is the negative button. That's for the negative from negative 4x. in the calculator, I don't have to type in -1 times 4x because 4 to the power of x, because the calculator knows the difference. So that's negative, then I push 4. Then I've got to go to my exponent, right? This button is one button to the left of 7 and then one button up. That's our exponent button. Okay, so -4 exponent button. And you can see in the calculator, you can see, well, it's y equals -4, but now your cursor is up here, right? That's where the box is. Well, just put your exponent of x in there. So the x button kind of looks like this. It's x, but then it's got y, z, and t, and then a, b, and c right there. And then when you do that, then the cursor is going to show x. And that's really all I want right there. So I'm going to push enter. Enter. It says on my screen, it says start.
So we should still have this minus.
All right, so I'm going to start with,
-1.
well, yeah, let's start with -1. Okay, because in my table I have -1, right? So I'm going to say start at -1. I push enter.
And
Step. I just want my steps to be by ones. If you wanted to show fractional value, you could, and it would be happy to do that. But I'm going to show it as ones. And then just below that, it says auto. So when I push enter for step, it says auto. And then over here it says ask x. So it looks like you could get the calculator to ask for the x, but I don't care. So I'm going to push enter, and then it's going to go down to OK. And I push enter again. Voila. Now the table is showing this as -1/4. So I have -1, -1/4, 0, -1, and 1, -4. You can scroll up or down. So if I push up on my cursor, the oval in the top right, then I can see what the y is for -3 and -4. So at -5, it's not showing the fraction there, but it's showing the decimal. And I could go down if I wanted to see what the y value when x is 10. -1,048,576. That's what it's saying on my calculator. You can go up or down if you want. You can try to go left or right, but it's not going to go that far. But. All right, so this graph, it does have an x plus 5 in the exponent. That's not a problem. And it's especially not a problem for the calculator. But I would just use a calculator to solve these values. Now, what we see is if we start with an x value that's 0, then we get as our y-intercept, we would then have 1/2 in parentheses to the power of 0 plus 5. Now, what this gives me in my calculator was 1/16. That's very close to 0. And if you go up 1 by chance, then you would have 1/2 to the power of 1 plus 5. You see what happens here is it makes that fractional value, the decimal, it's going to make it even smaller, is 1/32. Now the decimals on these is, it is pretty ridiculous. 1/132 comes out, I'm rounding, but 1.02, and then 1/16 it gave me as 0.03 rounded. Which, again, it's just showing that it's getting really close to 0. So if we were to go down this table, it would get closer and closer to 0. Can I put these values on the graph? Sure, I can. 0 and 1/16, it's still pretty close to 0. And then 1 and 1/32. Again, it's just a little bit closer to 0. And those 2 points that I put on there, the purple and the green one, that may not be obvious that it is getting closer to 0, but it is. Now, in my calculator, I'm using the table function on this one, so I don't have to do it so many times on the calculator, but I've got an x value that's -1, and then again, I'm rounding. That would be 0.06. So it's almost a half at -1, right? A little bit more than a half. About right there. And if I scroll up, it's showing as -2, and then 0.125, -3, and 0.25. And then if I go up even further, I need some more values there, but it's showing as -4, 0.5. And then also when x is -5, then we get 1. And I'm going to show why that's the case, why -5 as an x value specifically gives us a whole value right here. But again, let's see what this is. Let's get these points on there. So I've got -2 and about an eighth. I went too high on that orange point, didn't I? So let's put that one in its correct position. I had 0.06. I put I had 0.6. That was incorrect. So again, it's very, very close to 0. Negative 2 and 1.5, again, it's 1/8, so, you know, still very close to 0. Negative 3 and 0.25, again, it's not really too far from where I have those other ones. Negative 4 and then 0.5, that's a half. Negative 5 and 1. All right, now we're starting to see some progress. In fact, if you were to go up even one more in the table to negative 6, then you'd see that that value is 2. So negative 6, 2. I think we can do another one, yeah. Negative 7 shows 4, so negative 7, 4. I'm just using the calculator for these values. And negative 8, 8. I can fit all these on there. Okay, and now we see a nice, smooth, curved pattern. And I'm expecting this to get close to 0 because the C value up there, it would have been plus phantom 0 right there. So the asymptote is going to be at 0, and that's nice. But now that I have all these points, let's go and draw the graph for this. Let's see if I can do it. So I'll start at the origin. Let's see if I can. I'm just kind of trying to make it look pretty. It's not bad. And then to the right, it's just going to get closer and closer to the x-intercept. That's okay right there. So that's the graph that I got. It may not be perfect, but it at least has all the points on the graph that I have from the table. So over here, we got negative 5, 1, right? Why did that work? Well, the original equation was 1/2, which I don't really care about the base, but the exponent is x plus 5. And the reason why we get a full value there is because when you replace that x with negative 5, that is where the exponent begins to be 0, right? So it really ends up being 1/2 to the power of 0, which is 1. Now, if we go through the table, why does 6 give us 2? Because now you'd get a negative exponent. So this would produce still a base of 1/2, but then it's to the power of negative 6 plus 5. Well, why does that negative exponent give us 2? Because that being negative 1 flips the fraction to 2, and it makes it 2 to the power of 1. So as this gets, as the negative becomes bigger, so if this was negative 2, then you'd have 2 to the power of 2, which is 4, and then that's how we get to 8, and then you'd get 16 and so forth if you were to move up the table on the graph. So when you get, what this means is that when you get fractional bases like we did here, you'll get whole values if you, and this is only if the numerator is 1, but when you get 1/2 like this, you can make these whole values simply by making the full exponent negative, which is why we would say, well, maybe we start with negative 5, then we would try negative 6 and negative 7, and then we would get these values as we go down. So that's another reason why it's going upwards. The more negative the x becomes is because it's flipping that fraction to become a 2. So for this one, it says find the asymptote and the y-intercept, no problem, okay? Because I know the asymptote, since we're looking at these exponential equations, it's got to be y equals, remember it's that c value, whether it's being added or subtracted. I can see it right there in the equation. It's being subtracting that 3, which means that right now at y equals 3, that's the equation, would produce this line right here, a horizontal line, where the y is negative 3. Now you can put arrows on that if you'd like, but we don't necessarily need them. And again, why is that negative 3? Because I can get this term, 5 to the power of x, to get very, very, very close to 0. Like if you made x negative 100, it'd be so close to 0, the calculator would think that you wanted 0. So this term I can make this as close to 0 as I want, and then 0 minus 3 would be negative 3. That's why we have this asymptote line right there. So that's the equation, y equals negative 3. The y-intercept, of course, is just where the x value is 0 in the actual function. So that means that for the function that we have, f of x, this would then be 5 to the power of 0 minus 3. Now 5 to the power of 0 is 1, 1 minus 3. would be -2. So I have a y-intercept at 0, -2. Okay, now for the graph, we're going to need a table. I'm going to do this by hand, probably, even though I should just use the calculator. If you can use a calculator, I would suggest that you do because it wants to. So for these values, I'm going to do the same thing that we've been doing. I'm going to choose a nice value of x, like 0, which we've already seen that value, right? We know if we chose an x value that's 0, we had -2. Fair enough, but let's put another one on there. Let's make x 1. Okay, so that'd be 5 to the power of 1 minus 3, which would be 5 minus 3, which is +2. So I can put this on the graph at 1, 2. It's an ordered pair. 1, 2. Nice. Let's put another one on there. Let's see if we can fit another one. I'm going to choose an x value that's 2. So that'd be 5 to the power of 2 minus 3. We're not going to fit this on the graph because it's 25 minus 3, which is 22. Okay. So it's going up very quickly. Like I said, it'd be nice to have a third point on this to work with. Let's choose x is -1. So that would be 5 to the power of -1 minus 3, which would really be 1/5 minus 3. So -14 fifths. And yeah, the fraction's not going to help us. Let's make that a decimal instead. That'd be -2.8. So with that one, then we get -1 and -2.8. Again, see how that point puts us already very, very, very close to the asymptote. Now you could try -2, but again, you're going to get really something that's very close to -3 on that, which means we're ready to draw this graph. So let's see. Yeah, I should go through that point and try to do this pretty good. Yeah, that's not bad for me. Okay, but I've got to go up the graph as well. So,
According to the table, all my numbers
Something like
match
this.
up except.
So you can see, I mean, you wouldn't want me doing brain surgery because of this line right there, but I've done worse. A bank features a savings account that has an annual percentage rate of R rate is 2.8% with interest compounded quarterly, and quarterly means 4 times a year, just in case we were wondering. 4 times a year. Brody deposits $3,500 into the account. Hey, what values should be used for P, R, and N? Yeah, we have enough information for that. That's nice. So P is the principal. That's the value that you start with, the value that you put in the beginning. Brody's going to put in $3,500. Now, we don't have to label this because it's just asking for the value of P, not its label. The rate that was given was 2.8%. Now, 2.8% though, we would want this to use this as a decimal. So 2.8% would mean that you'd have to move that decimal 2 times to the left, which would then make the rate 0.028. N is the number of times that it's compounded annually in this case. So since that's 4 times for us, it's quarterly, it's going to happen 4 times. There's our values there. Next up, part B says, how much money will Brody have in the account in 9 years? So this is the way this works. It goes back to compound interest, which you learned in 990. Here's a nice review, though. So it takes on this format. It says your future amount will be the principal. Now this one, that means that you start with 100%. And in this case, then you operate on the rate. Now, the reason why I'm leaving this blank is because if the rate goes down, then you'd subtract. If it goes up, then you would add. So I'm going to leave that blank. For this problem, of course, you're getting this 2.8%, so we are going to use addition.
Is that a 1
A 1. And then this is to the power of t, well, T is for time, that's how many years it's going to occur. Which, for this one, it's kind of N. So this is gonna work a little different. So here's how this works. P is principal, that's fine. We got $3,500, $3,500. And then we take the 1. Like I said, we know that we're getting this savings account that has an annual percentage rate. They're adding this value to your account. And the rate we know is 0.028. Sorry, that's kind of small. Now, why did I put that there? It's because that's for a full year. The rate is for a full year, but this one is occurring 4 times in a year, so we're gonna have to divide that by 4. All right, then the time that they gave us for the time, it's 9 years. So it is to the power of 9, but that's just annually. We know this is occurring 4 times every year, so we'd also have to take the 9 and multiply that by 4. This is something that I can put directly into the calculator to find this value, so let's do that. All right, so part by part, let's do the addition first because I have to do the order of operations. So 1 plus as a fraction, 0.028, or just division, whatever, divided by 4. So this gave me 1.007. Then by the order of operations, I'd do that to the power of 9 times 4 is 36. So that's to the power of 36, enter, and it gave me this really ugly decimal. 1.285467023. There's more to it, but the calculator's just not showing it. We're going to take that 3,500 and multiply that, and that will be our final answer. So times 3,500, and I end up with 4,000. So yep, 4,499, and this is money, so I'm going to round to the nearest hundredth, 0.13. Now the answer is not $44,099.13. Well, it is. I'm sorry. It's not just 4,499.13. Make sure you label it because this is a word problem, which I have done. That's it right there. There is if your bank is paying you 2.8%, the real question you should be asking is, what are they making? Find the amount of money in an account if $9,100 is deposited at 7% interest compounded weekly, and the money is left for 9 years. So the same number of years, different amount of money, different interest rate. All right, so let's take again the formula. The future value, which is usually shown by A for an amount, is going to be the principal. Then it's 1, because that's 100%. We're going to add the interest rate for this problem. And then it would usually be to the power of t. And this is where is the foundation for this formula that we're using. The principal we have found. We know that's, you're going to start the account with $9,100. Okay, so I got that. And then I'm going to multiply it by my rate of change. Again, the 1 represents 100%. Now, that's going to be crucial because that's why it's there. It's not just the one that's randomly there. You start with 100% of what you have, then you add the percentage. In the past, with percentages of changes, usually you would find the percent of the value and then tack that on at the end. This allows us to do it through the percentages in the beginning instead. So it's 1 plus the rate. And the rate that they gave us, 7%.
7.07. 0.07.
Yeah, so 7%, that would move the decimal 2 times to the left, which would make this 0.07. So let's get that in there, 0.07, that's 7%. And then the time here is 9 years. Now, this is actually not the equation, because they did say, look, we're going to do this compounding weekly. So I'm going to say the weekly here, there's 52 weeks in a year.
What if you didn't know that for a test?
So yeah, it's going to do this 52 weeks a year. Now the 7%, that was the annual interest rate. I guess they didn't really say that, but either way, the percentage that they give us is going to be annually. But this is gonna happen 52 times in a year. So I'm gonna have to take that 7% and divide it by 52, because there's 52 weeks in a year. And the 9, since there's 52 of those in 52 weeks in a year, we'd have to multiply the 9 by 52 as well. Now that may seem kind of large, but also the percentage is reduced by division of the 52 as well. So it doesn't come out, I mean, it may look kind of nasty, but it doesn't come out too bad. Now this one, I'm not gonna do it part by part. I'm just gonna put this into the calculator. 9,100 parentheses, 1 plus, I'm gonna use the fraction N over D button, 0.07 over 52, close parentheses, to the power of 9 times 52. And the 9 times 52 is in the exponent function of the calculator, but it looks like it spits out for me. It spit out
9,210.
17,000.
$79.02.
$79. Yeah, rounded, this would be 2 cents. Thank you. And don't forget to label these when you're doing them by hand, but we did it.